All right, today we're learning how to graph kind of our general rational functions. There are simpler cases of these and they can get really, really complicated. We're going to be keeping to a little more than the simpler cases, but we're not going to go crazy complicated either. Okay, so the first thing we want to do for these rational functions, like we'll be doing the whole chapter, is start by completely factoring the top and bottom. Okay, so factor everything out. And then we're going to look for things that are called asymptotes. This is a new word that we've seen, or first time we've seen this word. And an asymptote is typically a line or function that our graph will get infinitely close to, like keep getting closer and closer. So for instance, I might have a graph that's curving, and it might be getting closer and closer and closer to that dashed line forever. Okay, so that would be a value called an asymptote. Sometimes they're vertical, sometimes they're horizontal. They can be at an angle, sometimes called slant asymptotes. Or you can actually have an asymptote that is like a parabola, and your graph starts curving closer and closer to that function of the parabola forever. So anyway, that's what an asymptote is. It's a value, function, line, whatever you want to call it, that our graph will just keep getting closer and closer to. Okay, so to identify when we have vertical asymptotes, if we do, and or what's called a hole, we're going to look at the factors in the top and bottom. Okay, if the top and bottom have common factors, factors we can cancel out, we're going to go ahead and keep the domain of the original function, right? Remember we did that all along. We can go ahead and simplify it though before we graph it, which is nice. Okay, any of those zeros in the denominator, values that were in our domain, that canceled out, like if a factor ended up canceling out, that ends up becoming a singular discontinuity, usually referred to as a hole, like a singular hole in my graph, where my graph might be going along and then it kind of skips a point and then continues. Okay, we call that a singular discontinuity, right? One value where it's discontinuous, or sometimes just called a hole in the graph. And those would not be representative of vertical asymptotes. Okay, so typically we're talking about values in the bottom. So before we even get to this second part, let's go and do an example to start with just talking about our vertical asymptote and or holes. Okay, so for our first example here, identify all asymptotes, state the domain. Okay, so it says to first start by factoring completely. We might note in number one, there's pretty much nothing we can factor there. Okay, I can think of the bottom, I guess, as its own factor, x plus 4. And then we can state our domain. Well, we know from before that in this case, our domain x can't equal. So for our domain, could be all real numbers as long as x does not equal negative 4, right? There's our domain. Since there's no factors that cancel between the top and bottom, that means that this graph does not have a single hole in it. Instead, the values that make our denominator 0, if it doesn't cancel out with something in the top, that is also a vertical asymptote, which we'll abbreviate VA. So when x equals negative 4, we're going to have this kind of vertical line that my graph will curve away from. Okay, so we'll look at that graph in a second. Okay, so here we are on Desmos. We've graphed our function to take a look at it. Oops, sorry, this should have said plus 4. Yep, now I have it correct. Now I can look at my function, and we're going to see if we graph the line, the vertical line, x equals negative 4, and we check, I'm going to drag my graph here, we can see that my graph starts curving closer and closer and closer to negative 4. And in fact, it will get infinitely close to negative 4 as our graph goes up forever and down forever. So that is what a vertical asymptote is, kind of this invisible line that our graph is curving closer and closer to. Okay, so likewise, before we move on to the other part there, let's try to find the vertical asymptote for our next graph. So again, we would try to factor it. Doesn't look like anything in the top and bottom factors. So let's write our domain. The value that would make the denominator 0 Right? Remember, if you need to, you can stop and set that equal to 0 and solve. And we know when x is 3/2, the denominator is 0. So we can say our domain is that x could be any real number except 3/2. Now again, since nothing cancels between the top and bottom, that restricted value on our graph represents the vertical asymptote, is that x equals 3/2. So we can take a look at that graph really quickly. Okay, so here is our new graph. Let's confirm we have the correct vertical asymptote by graphing this. X equals 3/2 or 1.5. And I can see, yeah, kind of checking, my graph does look like it's curving closer and closer to that vertical asymptote. Okay, what about in example 3 here? Let's see if we can factor some of this out. And sure enough, the top is a factorable quadratic. That factors as x plus 2 times x plus 3. And the denominator is our difference of squares, x plus 3, x minus 3. And we do have this minus 3 after our fraction. Don't worry about combining these fractions for graphing. But here's our function factored out. Now note, we're still going to write our domain. The values that would make our denominator 0, right? Exclude those from the domain. So we know x cannot equal -3 or +3, right? -3 from this, +3 from this. Okay, however, notice that we can cancel out some common factors here. In fact, this factor, x plus 3, can be reduced. And in fact, if you were finding points by hand, you could now kind of graph this or calculate all of your points from this simplified version, as long as we skip the domain values from the original. Okay, which is nice. However, that also tells me something different. Instead of having 2 vertical asymptotes, which is possible, this one, the value here, remember the 0 from this would have been -3. That value, x equals -3, is a hole in the graph. It's not a vertical asymptote. So we have one vertical asymptote, but it's the other factor, the one from the x minus 3. X equals +3 is our vertical asymptote. -3 does not represent an asymptote. This represents a hole or a singular discontinuity in our graph. So let's take a look at what that would look like. Okay, here is our graph. Notice, even if I zoom out here, I can see there looks like maybe our vertical asymptote at x equals +3. Graphing that line in, we can confirm that. But we don't see one at -3. In fact, there doesn't even look like there's a hole at -3, and that's a limitation of most graphing utilities. There's actually only one that I know of that will show you that hole without looking at a table. So we're going to click the cog here and turn our function into a table. Okay, if we do that, and I type in the x value, -3, I can tell that it's undefined there. Meanwhile, get rid of that one. At +3, it's also undefined, but one of these is a hole. My graph is actually just skipping that microscopically tiny point, right? And then continuing, whereas at +3, that undefined value represents a vertical asymptote. So they're both undefined, but our graph is doing very different things over them. Here, it's just kind of jumping over the point and continuing its curve, and here it's kind of curving towards our line forever, right? Just as a quick second example, this is some of the software I sometimes use to generate worksheets called CUDA. Anyway, this graphing software does, when you graph these, show you visually the discontinuity. So you can actually see that open circle there, and that's what we would draw this in by hand as. We can see our vertical asymptote there, and there is a horizontal asymptote to this graph. We're going to talk about that in a second. Right now we're just focusing on the vertical one and or holes. Okay, let's do that for this last one over here, number 4. Nothing to factor really out at the top. In the bottom, I can tell we can take out an x as a common factor. And I believe that quadratic down there is actually factorable as well. X minus 5 and x plus 1. Okay, so if you factor that all the way out, oh, this is 3 times x. Okay, so we might have something to cancel in the top and bottom. Let's look at our domain. Remember, x cannot equal, from this factor, 0. From this factor, negative 5, or sorry, positive 5. And from this factor, negative 1. So 3 restricted values. Let's figure out which ones are wholes and which ones are asymptotes. So here, this single x is a common factor. So we actually can cancel those out, which means at 0, this is not a vertical asymptote. This is a hole in my graph, or a singular discontinuity. These other two, though, will represent vertical asymptotes. So this graph has 2 vertical asymptotes at x equals 5 and x equals negative 1. So obviously that's going to look much stranger. Let's take a quick look at that graph just to confirm all of these things. Okay, here's our graph from CUDA. So you can see, very strange looking graph, but we can confirm here at x equals negative 1. Yep, I can see my graph is curving away from that line. And it looks like at x equals positive 5. Confirm that those are 2 vertical asymptotes. However, remember, 0 was a restricted value, but we can see it is not an asymptote. Now again, I would have to look at a table of values here, but I can see that at 0, my graph is also undefined. So it is just a singular hole in the graph where it's kind of jumping over and continuing, whereas at the other one it's kind of curving away from and getting closer and closer to, but never equaling. Okay, here's that same graph in the other graphing software here, but you can visually see that hole at 0. Again, remember that was from the factor of x that canceled, that is a hole, and the other 2 restricted values represent vertical asymptotes. Okay, this does mean that you can use the simplified version of this graph to continue calculating points. If you needed to plug in x's and calculate y's to find points by hand, to calculate all of your points, you just need to, of course, skip those restricted values. So before we move on, let's go back and talk about the other possible asymptotes. Okay, so sometimes they are horizontal lines. More often than not, they will be for us. But there are other asymptotes, like slant asymptotes or other functions. So the horizontal or other asymptotes are a little more difficult to figure out. But please know that all of these properties come from just doing polynomial long division. So in a pinch, if you forget these, you can just take the top function and divide it by the bottom function and do polynomial long division, right? Where you take the largest in each, you divide those off to the side, like 4x squared divided by 2x squared, and this gives me, oh, the constant of positive 2. And in fact, y equals 2 is generally going to be our function. There's a little bit more to it than that, but we'll talk about that right now. But again, all these properties that I'm about to show you all come from long division. Okay, so we're going to look at the degree of the polynomial in the top and bottom. Usually it's okay to look at the original, the unfactored one, because it's easier to see their degrees. If the top and bottom have the same degree, now this is again just a shortcut to long division. If they have the same degree as we just saw, you can use the ratio. So what I mean by degree, of course, again, is that the highest power of x, or degree of x, right, is the same in the top and bottom. These are both x squared, so that is the same degree. Degree 2 on top, degree 2 on bottom. Okay, so when the top and bottom have the same degree, we can use the ratio of their leading coefficients, 4 over 2. So normally, we would just write y equals 4 over 2 or y equals 2. That is where my horizontal asymptote will be at. Okay, however, sometimes they're going to put in this plus 1 or some kind of k value after my function, right? Remember with a, h, and k always shifted my graph vertically. Well, this plus 1 does the same thing. It moves my graph up, all of my points up 1 vertically, including this horizontal line at y equals 2. It gets shifted up 1. So it ends up being at y equals 3 for this overall graph. Okay. If that plus 1 wasn't there, it would have been at y equals 2. But as you can tell, we finished calculating that. It would be at y equals 3. And we'd call that a horizontal asymptote if it's just y equals a constant. Okay, so we'll try some of those. Okay, so let's take a look here. We're going to skip straight to example 2, which is one of the examples where the degree of the top and bottom is the same. Right? If I look at the degree up top, this is x to the first, and the degree of the bottom is x to the first. They are the same degree. And so, as it said earlier, we can look at the ratio of the leading coefficients. So if I look at the number in front of x, here is 1, here it's a 2, and if we do that fraction, y equals 1 over 2, we get y equals 1/2. That is where our horizontal asymptote would be. Now we should look for that kind of plus k value, but you might note that this one doesn't have a plus 3 or a number afterwards, right? So you can think of it as plus 0, right? There's no k value for this. So y equals 1/2 is our horizontal asymptote. So if we look at that graph again, okay, so here's this graph again, and we have the vertical one we did earlier, x equals 3/2. So let's try graphing this horizontal one, and we can kind of visually check. So it should be at y equals 1/2. So let's check that out. Y equals 1/2, or of course 0.5, whichever way you'd like to put that in. So I've graphed it. I can kind of pan to the right, and yeah, look at that. It looks like it's getting closer and closer to 1/2, and same thing to the left. So that does confirm it does have a horizontal asymptote, and we've found the correct value. Yeah, another one on this page, let's take a look at example 3. Also has the same degree in the top and bottom, 2 over 2. These are both second degree polynomials. And again, because they match, we can use the shortcut of looking at the numbers in front, which in this case is 1 over 1. However, this one does have a k out here, which will shift it from 1 over 1. So my horizontal asymptote would be y equals 1 over 1 minus 3, or 1 minus 3, which is at -2. So we'll take a look at this one and hopefully confirm our horizontal asymptote ends up being at y equals -2. Okay, so here's that graph with our vertical asymptote at 3. Remember, it's undefined at -3, but that was just a hole in our graph. But let's try this. We said it should be down at y equals -2. So let's fill in that value, y equals -2. And yeah, look at that. I think we have calculated the correct horizontal asymptote. Okay, so we've looked at the case where the degree of the functions in the top and bottom were the same. We can do the fraction of their leading coefficients and then add or subtract k, depending on if it's plus or minus. Okay, what about if it's bottom heavy? The bottom has the bigger degree. Well, if you think about our long division, if I have some function like this, and I try to do long division with it, x squared, well, it won't go into x, right? I mean, if I try to simplify this, we have more x's on the bottom than we do in the top. We'd say this goes in 0 times, and in fact, that's why when the bottom degree is bigger, we'd say it goes in 0 times, it defaults to y equals 0. Now it would stay there, which would be the x-axis, if there wasn't a k value. So if there's no plus or minus after the function, or after the fraction, I should say, then it would stay at 0. Otherwise, we might have to shift it up or down by k. So let's take a look at a quick example that we just did on the next page. Okay, which would be, say, example 1 here. Now notice if the top doesn't have x at all, you can think of this as x to the 0 power. So this is a 0 degree, and the bottom is a first degree. So because the bottom has the higher degree, this would default to, and it is a horizontal line, y equals 0 plus k. And in this case, our k value is 2. Right, since it's plus 2, we're going to add 2. So our horizontal asymptote ends up being at y equals 2. We'll take a quick look at that graph again. Okay, so here was this graph. We'll go ahead and graph in y equals 2, suspected horizontal asymptote. And yep, it does, confirming that visually, match up with what we found. Okay, so third and final case here. What happens though if the top has the higher degree? If it is top heavy by degree, well, there's no avoiding it. We don't get to use one of these two shortcuts. We have to do the long division. The good news is I only need to get down to the constant. We don't need to calculate the remainder. Okay, but I would need to do polynomial long division, and y equals that answer is the equation my graph will get closer and closer to in the, it's not going to be perfectly horizontal. It might be a slant asymptote or a parabola or some other function. Let's take a look at one that will do that. Okay, and actually the first one, we could have done this previously, sorry. The first one to do that is a brand new example. Okay, so let's actually do this one from the beginning. We are going to, if I look at the degree of the top and bottom, it is top heavy by degree, so we will need to do long division here. But just to start this from the beginning, you could try to factor the top. Here again, a good check if this is factorable is if you multiply that over and made that 24. Are there factors of 24 that add up to 7? No. Okay, so it's not factorable. We don't need to factor the top out. So nothing cancels with the bottom then, because we couldn't even factor the top. So we have a domain. Let's do that first. Restriction that x cannot be -5. And because nothing canceled, that restriction does represent a vertical asymptote. Okay, so now I'm looking at the degree of the top and bottom. The top has the higher degree, which means this is a non-horizontal asymptote, and we have to do polynomial long division. So if we did this off to the side here, just remembering some of these steps. Okay, so we take the largest in each, and we're going to divide those off to the side. 2x squared divided by x gives me 2x. So we'd say this goes in 2x times. Okay, then we distribute our 2x times x and times 5. So that gives me 2x squared. 2x times 5 is 10x. Now remember, we need to subtract this entire line, and we did that through adding the opposites. So these cancel. We end up getting -3x. So I'll change colors there. -3x, and we can drop down the plus 12. Okay, well, check if we can divide these again. -3x divided by x. And yep, we can do this one more time, which gives me a result of -3. So -3. And once I get to a constant here, I don't need to go any further. We don't need the remainder. In fact, and we're going to call this the other asymptote, because it's not horizontal technically, will be at y equals 2x minus 3. That sounds crazy. Let's check if we got this right. Okay, here's our graph. I had to zoom out a little bit, as you can tell, to get a good look at kind of our different parts here. But let's check. Let's confirm our vertical asymptote is at x equals -5. And yeah, that looks about right. Yep. Okay, and I can tell our other one maybe a line. Let's try. We got y equals 2x, was it -3? Hey, look at that. How cool is that? You can see this graph is kind of curving towards both of those lines. That's pretty cool. Very weird looking graph, but we can find kind of these asymptote values that really help define a large portion of this graph, or kind of what shape we'll end up getting. Okay, just to go back and finish this one that we did earlier, if we were looking at degree for our other asymptote, the top is degree 1, the bottom is degree 3. So this is bottom heavy by degree, which if you remember kind of defaults to 0. So this would have been horizontal asymptote at y equals 0. There was no k value, so we don't need to add or subtract k, right? You can think of it as 0 plus 0, but y equals 0, the x-axis, in other words, will be our horizontal asymptote for that last graph. Okay, without making you go through and graphing things by hand or doing more examples of those, we'll do some in class, but we'll end the video here. Again, to review, vertical asymptotes factor everything out. Any domain restriction will either be a hole or a vertical asymptote. If the factor it comes from cancels, it's a hole. If it does not, it's a vertical asymptote. Okay, the horizontal or other asymptotes, again, these rules all come from polynomial long division. But if the top and bottom degrees are equal, we can look at that fraction in front of those biggest degrees, and then add or subtract k. If the bottom is the bigger degree, it defaults to 0, add or subtract k. And if it is top heavy by degree, like we did in that last example here, you need to do long division, and y equals that function is the equation of your other asymptote.